Okay, we're up to part 2 now of our rather long lecture about turbines. And one thing that, again, I wish your book had a chapter about turbines that would help, but we'll find some websites and so on that will be good sources of information for you. But one of the things I wanted you to know is that, broadly speaking, there's going to be 2 types of commonly seen wind turbines. And they go by the awkward names of hot and vaught. Hot means that it is a horizontal axis wind turbine, and vaught means that it is a vertical axis wind turbine. Both of those are practical. Both of them have pros and cons as to how we build them, and the marketplace decides what's the correct technology to use in a different application and so on. Hot, the horizontal axis wind turbines, are going to be the kind that you're picturing most of the time when we are talking about wind turbines, where the axis is horizontal and then the rotor is in a vertical plane. And there are lots of these kinds of technologies out there. There's the kinds that face upwind, there's the kind that face downwind, there's the kind that have 3 blades, there's the kind that have 2 blades, there are ones that are augmented, and so on. There's a lot of different technologies that can be used. We're going to see more about those augmented wind turbines later. But all of those technologies are based on this idea that there is a horizontal axis along which the rotor's shaft and so on is spinning. And that's a contrast to vaught, or vertical axis wind turbines, where, again, the turbine is rotating with respect to a vertical axis, and then the turbine is rotating around that axis, and these come in lots of different varieties. There's a lot of different technologies involved, all of which have pros and cons, all of which are used for different applications, and we'll see a little bit more about them as we go along here. But just be clear, there's a lot of different pros and cons, or advantages and disadvantages, to using hot versus vaught in different situations. There is no single one answer, like one is always better. It has to do with the application. Broadly speaking, though, if you're talking about vaught turbines are generally going to be closer to the ground, and so they are generally experiencing weaker winds. There's a grade school right here that has a vaught wind turbine sitting on its roof right there. Well, that turbine would undoubtedly be producing a lot more electricity if it were up on a 100-meter tower, but that's not what a grade school is going to be doing. It's also not all that really big of an area, the cross-sectional area through which the air is flowing, and therefore that is the kinetic energy that it could be captured by our turbine. It's just not all that great on these relatively small vaught turbines. So we would say that in general these vaught turbines have a smaller cross-sectional area than like a commercial hot system that would be producing power that goes into the grid. And so in general the amount of energy going into them is smaller. That being said, you certainly can make a very large vaught. Just to give you a sense here, this is in Ontario. Do you see how there's all these traditional 3-blade type horizontal axis wind turbines in this picture here? And then you see that one weird vertical axis wind turbine in there? This is a wind farm called, and I apologize, my French is terrible, and this is, it's actually in Quebec. I don't have any idea how to pronounce this correctly. It's Capshot, I believe is how you pronounce this place. It is in fact the tallest vaught ever built. The thing's 110 meters tall. And let's see if I have some other pictures of the thing here. Yes. So this is a very, very large vertical axis wind turbine here. And obviously it is capturing energy from a very large cross-section of area. The flux of kinetic energy is very large that it could be capturing here. And I really wanted to find some video of this thing running. And I kept finding these videos of people visiting Capshot and taking video of them on YouTube. And the turbine was never moving, but they were speaking French. I didn't know what was going on. It turns out that this turbine hasn't actually run since 1993 when an expensive bearing failed. There was no way to actually repair it in a cost-effective manner. So the thing only actually ran for 6 years. It is today actually all these other horizontal axis wind turbines around it are running. And in general, it's a tourist attraction where people can learn more. Like, kids go on school trips to Capshot and so on, and they learn about wind power. And in fact, there's a ladder up the central shaft there that people can climb. I don't think they let school kids climb, but you can climb, and it's a tourist trap now. Okay, but it's an idea. That being said, we still make lots of vertical axis wind turbines. They're just nowhere near on the scale of that one. Lots of places claim that they have the tallest turbines and so on. This particular picture seemed to be a relatively recent set of pictures of some they're helical versions of a Vought that are built by the campus of Texas A&M at Corpus Christi, which are 75 meters tall, and which they claimed were the largest vertical axis wind turbines in the United States. 75 feet rather, is about 25 meters. That's nowhere near the 110 meters of that very large Vought that was at Cup Shot. But I'm sure that this also collects a rather large amount of energy. Now, I want to spend a few moments real quick just on Vought technology, in part because so much of the rest of the lecture is going to be about HOT. There are a number of advantages and disadvantages to both of these technologies, but there certainly is one big advantage to Vought, and that is that the works of it are basically down at ground level. It starts becoming much, much easier to figure out how you're going to maintain this thing, because so much of its works are at a level that's not so hard to reach. Okay, think of all the works that are up there at the top of the tower of a wind turbine, of a horizontal axis wind turbine, and you realize that all that machinery and so on had to be put way up there, maybe 100 meters up, and people have to go up there to service it, and they have to have safety riggings and special training and so on. That is a big simplification when it comes to Vought. Another important deal that is a big advantage to Vought is that they don't have to face upwind. There's no business, again, there's some vocabulary about this in a little bit, but hot wind turbines are going to need to be able to turn so that they stay facing upwind. There's no such thing with the vertical axis wind turbines. They just sit and they spin in a given location without having to worry about like what direction the wind speed is. What direction the wind is coming from, rather. There are a lot of different designs of wind turbines in general, and Vought ones in particular, it seems. In fact, you can go on YouTube and see lots of different hobbyists and folks who try to live off the grid and things like that, who have built all kinds of bizarre Vought wind turbines. Broadly speaking, they come into two main categories. The first are these so-called Savonius turbines. And I'm going to go ahead and just admit, I'm not sure that it's pronounced Savonius. If you look on the different videos and so on, you see, or different websites, you see that sometimes they say Savonius, sometimes they say Savonius, sometimes they say Savonius. It looks like Savonius to me. So I'm going to go with Savonius. I don't know. Anyway, Savonius wind turbines are where there are like 2 to 3 cups or buckets or whatever, and they are rotating around a vertical axis, and they are producing mechanical energy that then can be converted into electricity or so on. And here you see some videos associated with them. And this can be a very simple technology. I mean, this can be literally like buckets cut into half and mounted properly on a vertical axis and so on. They can be as simple as like a cup anemometer. A cup anemometer is an example of a type of Savonius wind turbine. Remember, a cup anemometer works by producing a small amount of electricity through a little generator that's in there as it turns, and then a bit of electronics measures the voltage and so on the line that tells you how fast the wind is going. So that little cup anemometer there is a type of Savonius wind turbine. They are relatively simple and easy to maintain and can be left unattended for very long periods of time without engineers checking on them and so on, but they are not very efficient. Typical efficiency only runs about 15% with a Savonius wind turbine. You might remember that Betz's law says we're limited to about 59% of the efficiency, but there's a long ways between 15 and 59. This is not a very efficient way to produce electricity. It tends to be where you just need a small amount of electricity off the grid. Where this is going to tend to be the right application. You're not going to, produce enough power for, neighborhoods. You're not going to produce megawatts of power or something like that using a Savonius wind turbine. On the other hand, there's the competing technology, which when I watch videos and go to websites and so on, you see 12 different ways to pronounce this name. It looks like Darius to me. We're going to say Darius. I saw lots of videos that called them Darius wind turbines. We'll call it that. I don't know what the correct pronunciation of Darius turbines are. But Darius turbines are the ones that kind of have those C-shaped rotor blades that give it kind of that egg beater appearance as they spin. Sometimes there's 3 such blades, sometimes there's 2, etc. And you can see examples of that here. That giant wind turbine at Kapschat was an example of a Darius turbine. And when you watch these things spin, you can see how they, really get going, actually, in the wind as they blow. What's actually going on with the Darius wind turbine here is that those blades are actually shaped like an airfoil. They're kind of shaped like the cross-section of the wing of an aircraft, and as the air flows over that airfoil, it generates lift. Well, we would say lift if it was against gravity. It generates a force. On this particular diagram you can see here, as it is rotating in the direction you see the arrow is going on there, it's generating a force with a component in the direction of rotating the turbine. So the blades have this airfoil shape that gives them, once air starts flowing over them, they kind of create a force by extracting kinetic energy from the wind that makes the turbine spin. This is pretty slick, but in general they're not self-starting. Generally speaking, in order to get the Darius wind turbines going, you need to give them a push that at just the wind speed it's encountering on its own, it won't generate enough lift as the air flows over these airfoils to make the thing start turning. Any more than when you have an aircraft sitting on the ground, the wind blowing over the wings isn't going to be enough. The planes aren't going to just start like flying, right? You need to give them a mechanical push to get the wind flowing over them. Then they can maintain their own lift and so on. So generally speaking, these kind of Darius turbines either need to have some kind of electrical motor that gives them a start if they stop, like, if there's a break in the wind, then you got to have them restarted, or they have like these kind of hybrid designs where there is a Savonius wind turbine inside of the Darius wind turbine, so that when the wind stops, the Savonius wind turbine can start back up on its own, and that will give the whole Darius apparatus a kick, as it starts to turn, for it to generate its own forces and start turning itself and spinning in the wind. It's just engineering, okay? We can always find ways to solve these kinds of problems. There's actually a lot of weird problems with Darius turbines in terms of the actual design of them. The forces acting on each of the blades varies enormously as it goes through one rotation, because at one point it's going with the wind and not generating a lot of lift, and then on the other side, as it comes upwind, it's generating enormous amounts of wind as force as the wind is going across the blade at a higher speed. This creates a lot of engineering challenges. There's sort of a pulse to the stress exerted on each of those C-shaped blades as they go around the vertical axis. There are a lot of ways to get around that. Probably the prettiest one, just because we happen to already see some diagrams of them, if you have these sort of helical-shaped Darius wind turbines, the different parts of the blade are experiencing different amounts of force at different times, and it kind of makes the stresses that are being experienced on these blades more even, and that will help with with leveling the load of the actual aerodynamic load being experienced by the thing, and make it have a longer expected lifetime and so on. Another variation on the Darius turbines is the so-called gyro mills. Gyro mills have 2 or 3 kind of 8-shaped blades that spins about a vertical axis and so on. Here's an example of a gyro mill spinning here. And again, there's certain advantages to this in terms of like the direction that the different mechanical stresses are directed as the blades are rotating around the vertical axis and so on. This isn't an engineering class. We're not going to get all bogged down as to why. I wouldn't be the right guy to teach you how all the different forces at work here result in different mechanical strains and metal fatigues and things like that. That's not the purpose of our class. We're just kind of getting some vocabulary here to describe these different kinds of, in this case, vertical axis wind turbines. Alright, now before we move on to the third part of our lecture here, let's actually answer a couple quick questions. Question 4. On a Savonius turbine, the mechanism that keeps the turbine facing into the wind is expensive and complex to maintain. Is that true or false? Okay, so we're talking about a Savonius turbine. How does it stay facing into the wind? Is that a complicated or is that an easy problem? Alright, make a choice from those two options and get a little feedback before we move on to question 4.